Hello everyone, welcome back. So today we are going to discuss damped free vibration. So now in our last class we modeled undamped free vibration. So we have a single degree of freedom system, that means it has a spring attached to a mass of say m, and then there is a dashpot. This last component we ignored while we derived the solution in the previous class. So in this case we have only one degree of freedom x of t, and there is a forcing function, but for the time being we are not considering. The spring has a stiffness of k, mass is defined by m, and the damper has a constant c. So the equation we derived earlier, so m x double dot plus c x dot plus kx is equal to f, but because we are about to solve homogeneous part, that means the right hand side will be equal to 0. And there are initial conditions. So x at 0 is x naught, and the velocity, that is the first derivative of x at 0, is also defined. Now with this information we have to now solve this expression. The only difference in this case is the middle term that represents damping. So in this case also we will assume trial solution. So the trial solution in this case, x of t is equal to p e to the power lambda t. Now if this is the trial solution, obviously x dot of t and x double dot of t we can easily derive. So this will be p lambda a to the power lambda t, and the next one is p lambda square a to the power lambda t. Then the only task is to substitute these expression in the original equation. So if we do that, what we get is p lambda square e to the power lambda t in place of x double dot plus then c times p lambda e to the power lambda t plus k times p e to the power lambda t, which is equal to 0. Then we can further simplify this expression. So what we can do, we take this p e to the power lambda t common, and within bracket we have m lambda square plus c lambda plus k is equal to 0. Obviously again in this case p e to the power lambda t, this is not equal to 0, because in that case we will have a trivial solution. That means we have m lambda square plus c lambda plus k is equal to 0. Now this is a quadratic equation. Obviously we can find out the roots of lambda. So lambda in this case will be equal to minus c plus minus square root of c square minus 4 m k divided by twice m. So we can simplify this expression. So we have minus c by twice m, then plus minus square root of c by twice m whole square minus twice m inside the square root, it will be 4 m square. So, 4 m will get cancelled, we will have k by m. Now, if you recall, we also defined the natural frequency of the system. So, omega n is equal to square root of k by m. That means, omega n square is equal to k by m. So, we can substitute this omega n square in place of k by m. That we will do in a minute, but for the time being we have the solutions for lambda, and once we have the solution for lambda, then we can write down the complementary function easily depending upon the type of roots we have. So, in this case, if you look at the solution, there are 3 possibilities that we may encounter. So, there are 3 cases. Cases number, first case, c by twice m whole square is greater than k by m. In this case, we can actually replace this k by m as omega n square. So, this will be omega n square, which means c by m is greater than omega n. So, that is the first condition. Now, if we have this condition, this is called over damped system. Case 2, when we have c by twice m which is equal to omega n. In other words, c by twice m whole square is equal to k by m. If that is the case, obviously this third bracketed term under square root will be 0. We will come to that. But if we have a condition where c by twice m is equal to omega n, we call this situation as critical damping or critically damped. And the third situation where we have c by twice m is less than omega n, and this situation is called under damped. So, we have 3 possibilities depending upon the nature of roots. The first case, c by twice m is greater than omega n. So, let us first consider that situation and see what happens when we have over damped system. So, for that, let us first once more define the cases. So, we have in this case c by twice m is greater than omega n. Now, if that is the case, obviously we can find out the roots, that is lambda. These roots are real and distinct. Recall what is the expression of lambda? Lambda is equal to minus c plus minus square root of c square minus 4 m k divided by twice m. So, if we have real and distinct roots, in this case we have lambda 1 and lambda 2. and they are, if I just write it again, c by twice m plus minus square root of c by twice m whole square minus k by m. Now, if that is the case, then we can write down the solution. So, solution in this case will be x of t will be a e to the power lambda 1 t plus b e to the power lambda 2 t. So, we have lambda 1 and lambda 2 from this expression. Then once we evaluate lambda 1 and lambda 2, then we can write down the complementary function. So, if we look at this equation, we have a and b, these are the two constants. So, our next task is to evaluate these two constants. How do we do that? We have the initial conditions. If you recall, x of 0 is equal to x naught and x dot of 0 is x dot naught. Okay. So, let us quickly solve these two constants a and b, and then we will see how the solution looks like. For that, let us first differentiate x of t. So, if we do that, we have a lambda 1. So, if we differentiate this expression, we have a lambda 1 e to the power lambda 1 t plus b lambda 2 e to the power lambda 2 t. Okay. So, we can satisfy the first condition. So, in this case, at t equal to 0, we have x naught, which is equal to a plus b. Then for the second case, we have x dot naught is equal to a lambda 1 plus b lambda 2. So, we have altogether two unknowns and two simultaneous equation, and then we can easily solve this. I just write the solution for a and b and leave it as a home task. You can just try it at your end. So, it will be a equal to 1 by lambda 1 minus lambda 2 within bracket and b will be equal to 1 by lambda 1 minus lambda 2, then within bracket minus x naught dot plus lambda 1 x naught. So, what we do? We first define the mass, stiffness and damping. Then once we do that, then the problem statement is defined. We also need to define the initial conditions. Then based on this mass, stiffness and damping coefficient, these are the system parameters. Once we define the system parameters, then we can find out the roots, that is lambda 1 and lambda 2. And once we do that, based on the initial conditions, then we can find out what is A and what is B. Once that is done, then we can write down the solution x of t. Recall, this is the complementary function, that is, it is the solution corresponding to the homogeneous part of the differential equation. That means the right hand side of the equation is 0. So, we have 1 by lambda 1 minus lambda 2 and then within bracket So, that is the complementary function we have for the damped free vibration case. Now, if you look at the right hand side, we have two exponentials, e to the power lambda 1 t and e to the power lambda 2 t, and we have the coefficients based on the initial conditions that we define, that means x naught and x naught dot. Now, if you look at the right hand side of this solution, you will see there is no oscillating component. If you recall the solution we did in the last class for the undamped free vibration case, the right hand side was sinusoids. So, as t progresses, a sinusoid will continue its oscillation, but here in this case, the moment we have a over damped system, first of all we have damping, and the damping value satisfies certain criteria which is marked here corresponding to over damped system. So, the moment we have an over damped system, then we have the solution which has in the right hand side no oscillating component. That means motion is not periodic. So, the first conclusion we have, motion is not periodic. Now, obviously, if you look at the roots lambda 1 and lambda 2, there are obviously two roots, two distinct roots, but if you look at the nature, the condition that we have, c by twice m is greater than omega n. That means, the quantity within the square root is always positive. Not only that, once we find out this, the value of this term inside the square root, we can also conclude that its value is less than c by twice m. If that is the case, we can further conclude that lambda 1 and lambda 2, they are negative. Now, if the lambda 1 and lambda 2 are negative, that means on the right hand side we have two exponentially decaying terms. So, that is the nature of the solution when we have a overdamped case. So, the solution is exponentially decaying. Okay. So, that is solution is exponentially decaying. So, as time progresses, so if we have limit t tends to infinity, x of t will be equal to 0. That is simply because of these two exponential terms on the right hand side, where lambda 1 and lambda 2 are negative. So, we can then further conclude the solution is asymptotic as t tends to infinity. So, it will start at t equal to 0, we will have these initial conditions that must be satisfied, because that is how we find out the solution. So, at t equal to 0, we have to satisfy x naught and x naught dot. Then as time progresses, then what will happen? It will exponentially decay and asymptotically reach to 0 line. We will plot that in a minute. Now, that is the solution of a overdamped case and the nature of the solution. So, let us plot the solution. So, we will have this is the horizontal axis where we have time and x of t is here. Obviously, it will start with x naught at t equal to 0, and this slope here is the velocity. Then as time progresses, obviously it will asymptotically go to 0. Now, before we move over to the second case, I will just draw your attention that in this case the plot shows that we have a positive x naught dot. Now, if we have x naught dot 0, obviously it will start with a horizontal slope and then it will gradually move towards 0 line. There is a third possibility if you have x naught dot which is negative. That means, at t equal to 0, the system has a negative velocity. So, it will go towards the negative line, and then I will leave an exercise, just check whether the solution can cross 0 line or not. So, that exercise I will leave it up to you to verify from this solution that if we have a negative velocity at t equal to 0, what will be the nature of the solution? Can it cross the horizontal line and come back? If so, how? So, that an exercise I leave it with you. Okay. So, that is the solution for overdamped system. Now, we have critically damped system. So, in this case we have C by twice m, which is equal to omega n. Now, before we find out the solution, let us first define critical damping. As you can see in this case, what will be C? C or C critical, we write C subscript C arc that represents critical, that is twice m omega n. So, that is called critical damping of a system. And if we have any other damping, say C, then the ratio of C with Cr is called the damping ratio. So, any other damping C we can represent in terms of critical damping ratio, that is twice eta n omega n. So, for critical damping, what is the critical damping ratio? So, in this case eta is equal to 1. So, if that is the case, then what will be the nature of the solution? So, we have lambda, if you recall, lambda is equal to minus C plus minus square root of C square minus 4 m k divided by twice m. So, our condition is C by twice m. So, minus C by twice m plus minus square root of C by twice m whole square minus k by m, which is equal to omega n square. Obviously, when C by twice m is equal to omega n, this part will go to 0. So, in that case, what is the nature of the solution? So, we can remove this part because it vanishes because of the critical damping, and the lambda 1 and lambda 2, both of them will have a value of minus C by twice m. So, in this case we have basically lambda 1 equal to lambda 2. So, you have two roots, but two equal roots, and not only that, they are also negative. So, what will be the nature of the solution? X of t will be equal to A plus B of t e to the power lambda t. Obviously, because lambda in this case is negative, on the right hand side we can identify we have a exponentially decaying term. So, as t increases, this bracketed term we have a constant a plus b t, but it is modulated by this exponentially decaying term. So, obviously, as t tends to infinity, we will again have a solution which is equal to 0. That will come in a minute, but for the time being, let us first find out the constants, in this case a and b. So, for that again we find out x dot of t. So, we have a plus b t lambda e to the power lambda t plus b times e to the power lambda t. So, what are the conditions we have to satisfy? Again x 0 is equal to x naught and then x dot 0 is equal to x naught dot. So, let us satisfy the first condition. In this case, we have x naught which is equal to a will remain as is, t is 0. So, this b times t will vanish. So, we have a times e to the power lambda t. So, this will be equal to 1. So, we have the first solution a which is equal to x naught. Then we can find out the second one. Obviously, x naught dot is the velocity at t equal to 0. Then on the right hand side we have a, b t will vanish times we have lambda plus b is the solution. So, this is equal to a is x naught. So, we have x naught lambda plus b. That means, b is equal to x naught dot minus x naught lambda. So, we can write down the solution x of t. In this case, in terms of initial condition will be x naught plus x naught dot minus lambda x naught times t e to the power lambda t. So, that is the solution for critically damped system. Again, in this case, what we can conclude that response is not periodic. So, we will have no vibration in this case, because on the right hand side we have no oscillating term. Not only that, what we can conclude, because of this damping which is satisfying this condition C by twice m equal to omega n, or in other words we have critical damping ratio which is equal to 1. Because of this value of damping, it ceases any vibration to happen. And on the right hand side, because of this exponentially decaying term, again as t tends to infinity. So, x of t will be equal to 0. So, we have a similar type of solution. That means, the response will start from t equal to 0 with the initial conditions that we set, and as time progresses, then it exponentially comes to 0. So, you can draw the nature of the solution. In this case, we will have a similar type as we noticed earlier. But in this case again, I will ask you to repeat the same exercise and verify whether the solution can cross 0 line or not, and then compare the nature with the overdamped system. So, that is an exercise. I leave it with you. Now, the third case is where we have underdamped system. That means C by twice m is less than omega n, or what we can write eta, that is the critical damping, is less than 1.0. So, if that is the case, then let us see what is the nature of the roots. So, we have lambda again is equal to minus C by twice m plus minus square root of C by twice m whole square minus k by m whole under square root, and we have omega n square is equal to k by m. If you recall, what is C? C is equal to twice eta m omega n. So, that means C by twice m, we can write eta omega n. So, in this case, lambda will be minus C by twice m, that will replace with eta omega n, and then plus minus square root of, this is eta omega n whole square minus omega n square. So, we can take this omega n square common. So, we will have minus eta omega n, then plus minus. So, omega n square, if I take it out of this square root, so it will be omega n, then it will be eta square minus 1. Obviously, in our condition we have eta is less than 1. So, that means eta square is also less than 1. So, in this case we can rewrite this expression as 1 minus eta square, and square root of minus 1 is I. Okay. Now, this quantity omega n times square root of 1 minus eta square, if you look at the expression, obviously eta is a dimensionless quantity, because it is the ratio of 2 damping, out of them one is critical. Then this quantity also have the same unit of natural frequency omega n. So, omega n, it is expressed in say radian per second. So, this quantity, it is called omega d. So, omega d is called damped natural frequency. So, then what we have finally, lambda is equal to minus eta omega n plus minus I of omega d. So, that is the nature of the roots. So, the first conclusion is that in this case we have two distinct roots obviously, but these are complex. So, now we have the complex root, and then we can write down the solution. So, what will be the solution if we have complex root? So, x of t in this case will be e to the power minus eta omega n t. So, that is the first part times c cos omega dt plus d sin omega dt. So, we have the complementary function. Remember, this is the case for underdamped condition. Now, in this case, look at the right hand side. Obviously, we have the first term which is exponentially decaying. So, this term is exponentially decaying. That means, as t tends to infinity, obviously, this will also come back to 0, and that is the nature of a damped vibration. So, it will start with some initial conditions, then it will keep on vibrating, and as the time progresses, obviously, it is bound to come back to 0 position. But the most interesting part is here in this third bracketed term. So, if you look at this quantity, obviously, in this case, we have sinusoids. We have cos omega dt and then sin omega dt. Obviously, because of these sinusoids, we will have solutions which will be oscillating in nature. So, we have three different cases. We started with the overdamped system, then critically damped system, and now we have the underdamped system. In the previous two cases, we noticed that the solution is not periodic, but in this case, when we have underdamped system, the nature of the solution tells us that we will encounter some kind of vibration. We will plot this in a minute and we will see how this solution looks like. But even before that, just by looking at the solution, we can conclude, because of this sine and cosine term on the right hand side, the nature of the solution will be periodic, and hence we will have vibrations or oscillations. Now, our next task is to find out these two constants c and d. So, we will do that in a minute. So, for that, what we do? We again differentiate this x of t. So, in this case, what we will have? E to the power minus eta omega n t, then we have c cos of omega dt. If we differentiate that, we will have minus omega d sin omega dt plus d omega d cos omega dt plus we have minus eta omega n e to the power minus eta omega n t, then c cos omega dt plus d sin omega dt. So, let us satisfy the initial conditions. That means, so the first condition x naught so this exponential of minus eta omega n t, for t equal to 0, this will be 1. Now, if we come to the third bracketed term, so this cosine term will be 1. So, we will have c here plus d times sin omega t. Obviously, this will also come to 0. So, we have the first condition identified. So, this is c equal to x naught. What about the next one? For that, we satisfy the second initial condition. So, we have x naught dot which is equal to d of omega d, then plus this minus eta omega n, and from the third bracketed term we will have c. Now, for c we can replace it with the solution that we have already obtained. So, this will be x naught. So, if we simplify this further, we have d which is equal to x naught dot plus eta omega n x naught divided by omega d. So, that is the solution for the constants. So, now we have c and d, and therefore, we can write down the solution. So, eta is less than 1.0, that is the underdamped system, and for that we have x of t which is equal to e to the power minus eta omega n t, then within bracket x naught cos omega dt plus x naught dot plus eta omega n x naught divided by omega d sin omega dt. So, that is the nature of the solution. Obviously, in this case again we can further simplify it. So, if we assume x naught is equal to r cos theta and x naught dot plus eta omega n x naught divided by omega d, this is equal to r sin theta. So, once we do that, we can further simplify this expression. So, this will be equal to r e to the power minus eta omega n t and then cos omega dt minus theta. So, what is r? R, if these two expressions you have, if you just square them and add them up, so you will get r square will be equal to x naught square plus this term eta omega n x naught divided by omega d whole square. And what about theta? Theta will be equal to tan inverse, it is the phase. So, it will be x naught dot plus eta omega n x naught divided by omega d times x naught. So, we have this is the amplitude and this is phase. So, if we draw the nature of the solution, so we have t and then x of t So, that is the first part, which is the exponentially decaying part. then it will start with some finite value. So, this is our x naught, and then so the blue line you can see is the solution, and this dotted line, this is e to the power minus eta omega n t. So, that exponential modulation is shown here by dotted lines, and within that modulation, so we will have the solution, and at t equal to 0 we have x naught dot. So, we can identify the time period here. So, if we start from here up to this point, this is the time period t. So, if you recall, t is equal to 2 pi by omega n. So, in this case we have under damped in this case we have vibration because of this initial conditions x naught and x naught dot, that is the displacement and velocity at t equal to 0. The system will start vibrating, but because of the damping, as time progresses it will have a exponentially decaying nature. And then if you look at t tends to infinity, because of this exponentially decaying nature of the damping, it will bring the solution back to 0. And that is what we also experience in day to day life, wherever we have a vibration. For example, if we experience an earthquake, although that is not a free vibration case, but because of the damping present in the structure, once it starts vibration, then as the time progresses, once the excitation is not there, then it still continues for some time. That is the free vibration part, but ultimately it brings back the structure to its 0 position, and that is what we get from our mathematical model today. So, we have solved 3 cases. So, critical damping ratio which is greater than 1, equal to 1 and less than 1. In the first 2 cases, we have no vibration. In the third case, we have vibration. So, the first one we call it over damped case. Second case is critically damped case, and the third one is under damped case. And from the mathematical solution, what we have noticed that in the third case we have roots which are complex in nature, and because of the presence of damping we have these complex roots, and the nature of the vibration is periodic, period is 2 pi, and then as time progresses, then it starts the vibration, then gradually comes back to 0. So, with that, let us close here our discussion on damped free vibration. In the next class, we will solve some examples and we will study the properties of this oscillation and what we can estimate if we have a response of a SDOF system. That will go through in the next class. Thank you very much.